Juan, okay, so I'm happy to introduce the second speaker of today's seminars. So we have Maria Lopez Fernandez from University of Malaga in Spain. He's a current professor at the University of Malaga. She has a long research career. Her most outstanding merit are the following. She was a postdoctoral researcher at the University Autónoma of Madrid with the Juan de la Cierva contract, and also has a contract at Superior Council of Scientific Research of Spain. She was a lecturer at Institute of Mathematics of the University of Zurich in Switzerland for 4 years, visiting professor in L'Aquila in Italy for 1 year period. She was awarded a Ramón y Cajal contract in 2013 call for application with service at the University of Malaga. She was a researcher and after associate professor at the University of Roma I, La Sapienza. She has been leader of research project in Switzerland, Italy, and Spain since 2013. She was awarded with the Leonardo Fellowship from BBVA Foundation in 2022 call. She has studied both theoretical and experimentally different type of partial differential equations with non-local terms in space or in time, with very diverse applications: fluid dynamics, mathematical biology, chemical reaction, acoustic, electromagnetism, finance, etc. Her main contributions include the application of advanced techniques of complex analysis to develop a new numerical method for approximating evolution problems with memory term. So today she will give a talk entitled Generalized Convolution Quadrature for Non-Smooth Sectorial Problems. So thank you very much for being with us, and you can start.
So thank you very much, Anna, for your kind invitation. I'm happy to have this opportunity to share a bit what is my line of research. So the title, for those who are not familiar with these methods, is might be a bit mysterious. So I will try to explain what each part of this title means: generalized convolution quadrature, what we mean by non-smooth sectorial problems, etc. So apart from the introductory part, the main results I'm going to present here have been obtained in collaboration with Jing Guo, who is now a postdoctoral researcher at Shenzhen University in China. She visited me and spent 1 year, and then she came again to visit me in Malaga a few years ago. And okay, so now she's working in China. So let me explain the type of problems that we study and where I have been working for a significant part of my career. So I'm going to start by introducing abstract time convolution. So this object here. So the problem we want to approximate in general, it has the following form. So we want to compute convolutions of this type from 0 to t, so Volterra convolutions, where we have a certain kernel K, and already I find a typo here. This should be an F here, so the problem should be given F here. Try to compute the result of performing this convolution, this C here. And in principle, it would be, we would like to approximate this quantity at times t1 up to a final time tn, arbitrarily spaced if possible, although this is not so trivial to achieve. So the step from uniform time points to arbitrarily spaced time points implies several difficulties that I will try to explain. So the kernel here could be many things. So that's why I say it's an abstract type convolution. It could be an operator, actually. So this kernel here could be even a semigroup, okay, that I write here like the exponential of AT, but this could be a semigroup, and A could be an operator. Think of the Laplacian, a second order elliptic operator, something very, very abstract here. It could be a distribution, Dirac delta, and this kind of kernels appear, for instance, when one is dealing with boundary integral formulation of wave problems. It can be something much simpler, such as a scalar functions like this. So this type of kernel, this appears when the kernel is this, what we have here is the fractional integral of the function that we have here, phi or f, sorry for this. And these fractional integrals appear, appear often in fractional differential equations, but you can have integral terms like this appearing as memory terms in other instances, such as problems with absorbing boundary conditions, or in models of viscoelasticity, where these terms like that appear inside as part of some PDE, okay? Maybe in boundary terms or whatever. And here I write another example where this kernel here looks still it can be highly oscillatory, okay? So it really depends on can be highly oscillatory when t is small here. So, and this kind of kernel can appear, for instance, if you are looking at the Schrödinger equation. So I mean, the range of applications can be large, and according to the application you are looking at, the analysis is different, and so that. But I just want to say that I will stick to this simple notation, but this can be many things. So in general, but the common things to all these applications is that one would like to avoid evaluating the convolution kernel here. So for instance, in this case, which is like the simplest one, for the rest of the talk, you might think that we are in this case is weakly singular. So applying a direct quadrature here for this kernel can be problematic, especially if you want to do this for a long time integration, and your function here takes values in some highly dimensional space. And you start having memory problems, stability problems, and so on. In some applications, it is actually not even known a priori, but it's the Laplace transform of this kernel what is known and is convenient to use. In many applications, this Laplace transform is known as the transfer operator. So this is the case when one is looking at wave problems. And it is also often the case that that one does not want to evaluate the convolution for a given data phi f, but one is given C, the left-hand side here, and wants to compute this phi here. This would be a density or something like that. So the problem is solving the convolution equation. So these two problems are very much related and can be solved numerically by the same family of methods. Okay. So let me deepen a little bit in the notation and reduce the focus to the to a certain family of problems. Okay, so it is convenient to use this operational notation. So this is convenient for the analysis so say we write the convolution with the kernel small k with f. We write in this way. We write the Laplace transform of the kernel evaluated at this differentiation symbol with respect to t applied to f. And the meaning of this is just that, okay? For your convenience, I write here the definition of the Laplace transform, okay? So the Laplace transform in principle is defined for set, a complex number, typically in a half plane with a real part of set bigger than a certain abscissa. And in this domain of definition, this defines an analytic function typically. Okay, so just here I try to clarify a bit this notation, noticing the following. So if you take the Laplace transform here in this expression here, the Laplace transform of the convolution is the Laplace transform of the kernel times the Laplace transform of the data, assuming that this is exists. And then in the particular case when k of z is set, it turns out that the result of doing this is the derivative of f if f of 0 is 0. Then we say f is causal. So that's one motivation to motivation to use this notation. Okay. In this talk, we are going to restrict to what we call sectorial problems. So here we assume that K is sectorial. And what does this mean? This means that the Laplace transform of the convolution kernel can be extended with analyticity beyond the typical half plane where this is defined to a sector including to a sector of the form argument of z smaller than p minus some angle smaller than pi half. So this means outside an acute sector around the negative real line. And we also assume that in the analyticity region, the norm of the Laplace transform, which could be an operator norm, is bounded in this way. So we assume that it has an algebraic, it can be growth, but in the applications I'm going to show, we are actually going to have a mu negative, so that it decays with respect to z when z goes to infinity. So the simple example is for the kernel here for the fractional integral, and in this case, the Laplace transform is just set to the minus alpha. So here we have a mapping which is defined in the entire complex plane, but the branch cuts. So here the angle here can be taken any positive theta k. In the case of the semigroup, when this operator A generates an analytic semigroup, and this is way more advanced, no? Then the Laplace transform is the resolvent of this operator, and the resolvent is also typically defined outside a sector of this way, and resolver estimates of this type are well known to hold. Also for discrete versions of these operators, if you think of a finite element discretization, for instance. So all this is well known in the literature. Okay, so this is the sectorial setting, and it's kind of better, it's easier to deal with because we have this extra regularity of the transfer operator. Okay. So the numerical methods I'm going to speak about, the convolution quadrature and what we call generalized convolution quadrature, are strongly based on the inversion of the Laplace transform, okay? So this really plays a role in the derivation of the methods and in the analysis. Okay, so the kernel, so assuming that assume that the kernel, that transfer operator here decays faster than 1/z at infinity, then you can replace the convolution kernel by the inversion formula of the Laplace transform. And this is given by this formula here, 1/2 pi I. This integral here along, in general, in principle, what you have is a Bromwich contour, which is a vertical contour running from the certain abscissa sigma minus I infinity to sigma plus I infinity. This vertical line here of exponential of zt times k of z, okay? The problem of using this numerically is that in principle you get high oscillations here, and this integral is not very good for numerical purposes. In the case of a sectorial transfer operator here, when you have this extra regularity region here, this contour can be deformed into a contour beginning and ending in the left half of the complex plane. And there you see that the real part of z goes to minus infinity when z goes to infinity along this contour, which helps this integral going to 0 when you move farther away along this contour. And then intuitively, I think it's easy to see that then this helps a lot numerically, because you can truncate at some point and then you reduce your integral to a finite interval, and you can devise probably nice quadratures for this, or you can work better with this integral. In the best case, this contour can actually be, I mean, the larger this sector is, the closer you can get to the negative real line, the closer your contour can get to the negative real line. And in some cases, you can actually degenerate this contour into the negative real line and derive what is called a real inverse Laplace transform. And this is actually one particularly favorable case, and I'm going to say more about this. This is some really classical stuff, can be found in the book of Henrici in the 70s. So the thing is that we can maybe exploit this property for some families of applications, both for the numerical derivation and the implementation of numerical methods. Okay, so this, as I said, we are going to so I go back to the object I want to compute, the convolution here, and I replace this kernel at t minus s by the inverse Laplace transform formula. And if I take outside the contour integral, what I obtain, I'm not writing the intermediate step of putting the integral with respect to s here. This y of set t is the integral in between 0 and t of the exponential of set t minus s times f of s. So it's actually the variation of constants formula for this scalar with respect to time value problem, okay? And I say with respect to time because this f of t can take values in some vector space, can be a vector if we are dealing with a PDE and we have degrees of freedom, and can actually be a function, okay? But looking at this problem only with respect to time, we see that this y solves the problem derivative of y with respect to t equal to z times y, plus f of t with the initial data equal to 0. And so now the idea is to approximate this quantity by the result of applying an appropriate ODE solver to this ODEs with parameter in the Laplace domain. Okay, so, and then you perform a first approximation. The first approach is, okay, we take a uniform sequence of time points, Tn, of the form n times h, and we apply, for instance, implicit Euler method here, or maybe something more fancy, a BDF2 or even a Runge-Kutta method. But whatever you put here you must be a bit careful, because this in principle is an infinite contour. So you cannot put here something which explodes with respect to Z. And that's why you are restricted to, in practice, to implicit methods here, so that this numerical solution has an algebraic decay at infinity with respect to Z. So this is what I say here. That sorry, I want to take this a bit further away. So that's why we will have in all these methods the underlying ODE solver will be implicit and A-stable. Okay, so when we speak, so this convolution quadrature, CQ here stands for convolution quadrature, and this is a family of methods introduced by Christian Lubich in the 80s. And GCQ here stands for generalized convolution quadrature, and is a generalization of these methods to variable steps, because the original theory for convolution quadratures is really limited to work with a uniform sequence of time points. So convolution quadratures and generalized convolution quadrature actually are also useful for non-sectorial problems. So in the first slide, I show you two examples of kernel, the Dirac delta and this oscillatory kernel that is actually coming from the Schrödinger problem. So, and in this case, the Laplace transform is only defined in the half plane, and it's actually allowed to grow algebraically, and these actually are more difficult to deal with numerically, especially if you want to do variable steps. But there is, I mean, this convolution quadrature has been intensively applied to wave problems, especially since 2007 or 8, and there are many papers on the topic. Although, as I said, not so many allowing to use variable time points. The analysis for decaying transfer operators for decaying kernel uses the contour integral representation of the error. So once we can represent our object, the convolution we want to evaluate as this contour integral, then this approximation we perform with this approximation here of the solution to the ODE can be put here, and then the error admits this kind of nice representation as this contour integral, and this will be nicer according to what you can do with this contour. And then, of course, this is only a first approximation step, but then we also need at some point to discretize this contour integral. We at some point need to choose one contour and devise a quadrature for this. And the success of the numerical method heavily relies on how skilled you are to develop special quadratures to approximate this in such a way also that they are not very expensive for every n, and you don't need too much memory with respect to the total number of time points you want to perform, which is actually one big issue here. If you look at this contour integral, I think it's not difficult to see that it's very important how is your transfer operator, so the analyticity region for this operator and how fast or it grows or it decays with respect to Z. But it also plays a role the choice of the ODE solver, because this determines the stability region of this method and the region where this is nicely bounded or not. Okay. Okay. So in this talk, I'm going to focus on the most favorable case, which is the case of transfer operators admitting a real inverse formula. So when you can degenerate your integration contour to the negative real line. So the assumptions is the following. So we assume that as a function of Z, although this can depend, as I say, on spatial variables, we assume this is holomorphic in any sector with the argument of Z smaller than pi. We assume that in all this domain of analyticity, we have algebraic decay with a power alpha in between 0 and 1. And you can say, okay, but it's better if it decays faster. Well, it is not, because close to 0, then you have a faster growth. So this is kind of the optimal behavior, close to 0, and when Z goes to infinity. Actually, if this power is larger than 1, we cannot have this real inverse Laplace transform. And we assume that this K is continuous in the upper half plane imaginary part of Z bigger than 0. Is possible with exception at Z0 and Z0, and similarly on the lower edge of the cut. So this will allow us to take the limit of K coming from above and from below of the branch cut, and in order to deduce a real inverse Laplace transform. So these hypotheses are kind of coming from the classical theory that you can see in this book by Enrici. So it's restricted. I mean, this restricts the class of transfer operators quite a lot, but still there are families of applications where this is the case, and I would like to mention them here. So for instance, the simplest one that I said, the fractional integral, when the Laplace transform is set to the minus alpha, when alpha is in between 0 and 1, this clearly satisfies this hypothesis. There are other instances. For instance, if you consider a kernel like this, but multiply by an exponential of minus RT, then the Laplace transform is this fractional power of z plus R, where R is this shift here or damping parameter. So you can find models in the literature where terms convolution with kernels like this appears as damping terms. And also convolution kernels of this when the Laplace transform actually is easier to write. You have a set to the alpha plus a positive number to the minus 1, and here the convolution kernel is not so easy to express. Is defined in terms of a Mittag-Leffler function. Okay, and these memory terms can be found in the literature. So for instance, in models for wave propagation in lossy media, so appearing as a adding term, for instance, in a wave equation, so such as the Westerveld equation, in case you ever heard. So there's a nice paper of Baker, Banjai, and Tashnik, where they deal with problems of this form with these memory terms. Also, the subdiffusion equation. So look at this fractional differential PDE. So if we have a omega, a bounded convex Lipschitz domain, the solution U of t belongs to H10 omega, to this linear subdiffusion equation that is the fractional derivative in time of this U minus the Laplacian of U equal to some source term here. And I'm hiding all the time the dependence on the spatial variables. Okay. And A is an elliptic sectorial operator, or a discrete version of it, a matrix, if you want. If you apply the method of line to this method, and you reduce this to a system of fractional order ODEs, then the solution to this problem is given by the convolution of the data F, the source term here, with a kernel whose Laplace transform is the resolvent of the Laplacian at set to the alpha. Okay, and then since the Laplacian defines an analytic semigroup, and we have nice estimate for the resolving of the Laplacian, it is quite clear that this operator here satisfies the assumption in the previous slide. Okay, so this is actually one of the applications we consider. So now I would like to say more about the numerical discretization. So I'm just going to, once we have an integral representation of the Laplace transform, of the inverse Laplace transform. So here, what I say is that if we have under our assumption, the convolution kernel can be written as the integral from 0 to infinity of the exponential of minus xt times a certain function g that you can obtain from the original transfer operator. So here we can get rid of the contour integral. And under these assumptions, we can bound the norm of this function, of this mapping here, by the m coming from the estimate of the original transfer operator, some constant x to the minus alpha. And then we can do the same trick I did before with the contour integral, but now with a real integral. And then everything is real, so we don't have any more complex set parameter. X is just real. And you reduce your convolution to the integral in between 0 and infinity of a certain function g here, whose behavior you are able to control. And the solution here, y, to this or this. So here I am not very consistent with the notation, because before I wrote here set and also set here, and now I write here x, and there is a minus x here. But for all the rest, it's convenient to get rid of the minus here. So this is maybe one could write a bar y here, but just to say that X here has the right sign for these solutions to be nicely behaved when X goes to infinity. And now with this representation of the thing you want, the object we want to compute, we can derive optimal error estimates, and also we can derive a good implementation strategy. So which at the end of the day are good quadratures for this quantity. So let me give you some results. As I said, the original convolution quadrature method was derived by Christian Lubik in the late 80s. It's restricted to work with a uniform time mesh here, and under assumption 1, and with a f here behaving like t to the beta, with beta bigger than -1. So we allow this function to have a singular behavior close to 0. The following error bounds hold. So if you apply the original convolution quadrature by Lubik to approximate this convolution, it turns out that the error estimate, and you choose implicit Euler for the solution of the scalar ODEs, it turns out that the error at time Tn can be bounded by t to the beta. So now it depends on how bad your data is. If in the worst case, when beta is in between -1 and 0, you have order, here 1 plus beta, but beta is negative. So this means that even away from 0, you don't achieve order 1. And close to zero, actually, you lose the first order, okay? Because you get tau to the alpha plus beta, and if alpha is smaller than 1 and beta can be negative, you might not get any approximation. For beta positive, the situation is a bit better. This error estimate says that point-wise, when you are far away from 0, you have order 1. And close to 0, when Tn is tau or twice tau or something like that, you have order alpha plus beta, okay? So you might see an order reduction close to 0 if alpha and beta are alpha plus beta is smaller than 1, okay? And in particular, this happens in this case, and if the f of 0 is different, it's non-zero. So this error estimate suggests that it makes sense to choose a time grid that is non-uniform and is denser close to the origin, where you have this singular behavior. Okay. The generalization of the CQ allows for an arbitrary time grid, and this is appropriate in this case. And in particular, graded meshes are quite a choice if you really know how the data is behaving, and you can adjust the grading of the mesh to this behavior. So the generalization of the convolution quadrature, we actually introduced for the first time this generalization analysis and so in 2013, but actually at the time we were looking at wave problems, so we were working in the non-sectorial case. We even developed higher order versions based on Runge-Kutta methods, but we kind of started from the most difficult problem. So let me show you the results, what we were able to prove at the time. And this theory has been revisited in the book by Banjai and Sayas, 2022. So if you are given an arbitrary time mesh, and we call tau max the maximum of the time points, we need to assume that the data f is of class C3, and we need to assume that f of 0 is 0 and f prime of 0 is 0. And actually, we need to assume quite a lot of regularity, even to apply the method, to justify that we can do this discretization. Then, if we discretize the ODE, the underlying ODEs with implicit Euler, the approximation we obtain the error can be bounded by T max times the norm of the norm of f in the CC. So we need 3 derivatives of f to be bounded. And actually, we even have an exponentially growing factor here with respect to time, where this sigma here is the abscissa of definition of your transfer operator. So we actually really need quite smooth data f here. And this means that the extension of f for negative times needs to be of class at least C1 in order to achieve, to be able to prove first order of convergence. This is under our especially good assumption 1. I'm not talking about the wave equation. There we need to assume a bit more. Okay, but since this analysis was designed for the wave equation, not for more favorable problems, we have refined our analysis, and what we are able to prove is the following. So we consider data f and assume that it can be expanded in fractional powers of this form here. So we separate the terms in bad powers, say, where these exponents here are small, and assume that there is some remainder here that can be nicely controlled. And what we are able to do is to derive error estimates for these terms here, for these bad powers, okay? And this was not possible with the original theory for the GCQ. So in particular, we are able to prove convergence of order 1 under this special assumption 1 for data f of t of this form when beta is bigger than 1 minus alpha. So this is really technical. We don't need to assume that f of 0 is 0 or f beta of 0 is 0. And then for worse values of beta, we need to ask for vanishing fractional moments, okay? But still, we are able to apply the method and to deduce these error estimates. And also, I'm not showing here the formula for the error estimates. We are able to derive an error estimate that is explicit for each time interval. And actually, this allows us to derive good error estimates for graded meshes, for instance. So here, for instance, I give you the result. So assume that the data admits an expansion in fractional powers as before, and we don't have f beta of 0 equal to 0. And this is often the case in many applications. And then we consider a graded mesh of this form with a grading parameter gamma. And then we are able to prove and actually to see how this gamma needs to be chosen in order to have convergence with full order for the underlying implicit Euler method here. So essentially, we need to take gamma proportional, gamma like 1 over alpha plus beta. And if we do so, we have essentially convergence of order 1. So 1 over the total number of steps we are doing. We can extend the analysis in almost straightforward to singularities located not at the origin, but at another time point. And I would like to mention that graded meshes are not the only possibility to resolve singular behavior. And actually, there is a nice paper by Banjai and Makridakis in 2022, where they derive a posteriori error estimates for fractional diffusion equations. And then they are able to do some sort of adaptivity where they produce time grid is not graded, is produced adaptively according to the behavior of the solution. And they are able to apply this grid because we have this GCQ theory below, okay? And also the implementation. So just to give you a flavor of the formulas and how the numerical object looks at the end. So this is the continuous convolution written in terms of this solution to the ODEs. This is the still semi-discrete convolution where we have replaced the solution to this ODE by the discretization based on implicit Euler. And here I am using the complex number here set. Here I am in the contour integral setting. And what we do is we solve the recursion for implicit Euler, and then this object is given precisely by this expression, this linear combination of the values of f with these products of the stability function of implicit Euler evaluated at the time points where we are approximating this thing. And then what we obtain is an approximation of the original convolution, which is a linear combination of the values of f with times some weights here. This is not there is no convolution structure here. These weights here are given by this expression here. We have in general a contour integral of the transfer operator times these products here. And the difficulty for the numerical approximation of this is that the poles of these products can be many. So this is a rational function with poles at 1 over the time step. And if we are playing with the time steps, the location of these poles can be, the poles can be located in a very large interval. In the real line, and this makes the numerical approximation of this integral complicated. Under assumption 1, the formula is simplified, and these convolution weights can be written as real integrals, so avoiding the contour integral and the complex arithmetic. And these products here are given by this expression, and actually since we are able to, there are no poles here anymore, if we are able to deform our contour here. So this becomes a much easier object to discretize numerically. So I would like to, how much time do I have? 10 minutes or something like that?
Yeah, I think so, yeah.
Okay, so I would like to say something about the implementation. So how do we compute these integrals? So the thing is that the same quadrature is not going to be good for all values of n and j. And there are reasons for this. So when the number of factors here is small, and this happens when j is close to n, this product does not decay very fast at infinity. And then it is actually not the best to integrate along the real line, but one can choose a closed contour in the right half of the complex plane enclosing the poles here. But if this contour that we choose goes very far away along the imaginary axis, say, when the imaginary part of set grows very much, then this can be highly oscillatory in some regimes, because actually these directional functions here are approximations of the exponential. As I said, when the grade is highly non-uniform and there is a big difference between the maximum and the minimal steps, the poles are distributed along a very large interval, and this makes things more complicated in the approximation of this integral. And in order to keep the complexity log linear with respect to n, because we do not want a method which complexity n squared or even worse, it is important that the same quadrature works for almost all j and n. So there is it's not so easy to solve this, but okay, we have worked on this for some time. So at the end of the day, the solution is to split this formula into a summation involving most part of terms, the all terms, so what we call the history term, and a short summation involving the recent history of the data here or the solution if you are solving the convolution equation. And this is what we call the local term, okay? And here under our assumption 1, this n0 can be really moderate, so 4 or 5. So this local term, which is more expensive to compute, is not so large, okay? And then, okay, how to choose the quadrature? So for the local term, we need to use a sophisticated quadrature that was devised by Nick Hale, Nick Heigan, and Trefedden, and it's based on a special elliptic function. This quadrature was thought for a different problem, for computing fractional powers of a matrix A and the log of a matrix A, but we were able to adapt this to this context. And so for the local term, we use the contour integral representation with a contour which is a disk, a circle in the right half of the complex plane. And for the history term, what we do is actually a not very complicated quadrature, because the integral is quite nice to approximate at the end. And the main difficulty there is to choose the quadrature in such a way that it works well for all values of n up to k, for k smaller than k minus n0. And here we basically apply Gauss or Gauss-Jacobi quadrature, and we derive careful error estimates to know how many quadrature points and nodes we need to use, okay? So at the end, the complexity is like n log square n, and we are able to keep the memory also proportional to n. So some references. So I would like to mention some references where we introduced this GCQ. The first paper was in 2013 for wave problems. The implementation was not so straightforward, and so we had to write 2 other papers for this. We were able to generalize this theory to higher order Runge-Kutta methods, and this theory has been revised for, at least for first order, by Lehel, Banjai, and Sayas, the late Sayas, in their book Integral Equation Methods for Evolutionary PDEs. And very recently, there has been some development of the GCQ for other formulas, the trapezoidal rule, which are particularly suited for hyperbolic problems. So let me just show you some numerical results. So here I consider the subdiffusion equation linear in a 1D domain, so not very complicated here. This is an academic sample where we have, yes, zero initial data. No, sorry, the initial data is in the domain of the operator, okay? And we consider homogeneous Dirichlet data. And the difficulty comes from the source term, which is singular with respect to time close to 0. And here our analysis tells us how we can choose a graded time mesh optimal so that we can achieve order 1. So in this case, the exact solution is known, it's given by this function here. And our theory predicts full order 1 if we choose a graded mesh with a grading parameter like 1 over beta, okay? And this depends on the behavior of f and on what we know about the resolvent of the Laplacian at set to the alpha. And actually, numerically, we see this quite nicely, okay? For many different values of beta, and for many different values of alpha, we always observe nice convergence with order 1 by applying the GCQ on this graded mesh, okay? So here, I just want to show you what happens if we use a uniform mesh in time. So this is the error. So this is space, so this is time. Here time goes to 0, so one see clears is that with the same number of time points, if you choose them uniformly, the error is much larger than if you choose the right grading parameter according to your data, where you reduce your error close to the origin by a factor of 10. And here we are not refining very much. Okay. So I would like to show you also, although this is maybe more technical, that the memory requirements are quite reasonable. So here in this table, we have in this here the total number of steps. So we perform up to 2 to the 10 number of steps, and for different values of beta, the smaller the beta, the worse. So the more singular your data is. We see that the total amount of memory we need, which is actually the total number of quadrature points that we need for the history term, remains nicely bounded. So it actually suggests, although it is not proven, logarithmic growth with respect to n, okay? And here we are actually choosing a very non-uniform grid where the ratio between the maximal and the minimal time points is really large. Is 30,000. Okay, and just one example where we have an ODE with a source term here where the singular, which is designed to be singular at 0 and at another time point that we know where it is because we are not doing an activity here, but we know that at some time r, there is some other singularity of also of algebraic type. And here, knowing where the singularity is and the behavior of it, we are able also to propose a nice time mesh, which is denser around the singularity point so that the final scheme converges with a slope, with a rate, with the order almost 1 and much better than the original CQ with a uniform steps. I mean, order 1 is already nice if your data and your solution is very little regular, which is the case here. So the conclusion, so we are writing then and generalizing this to high order Runge-Kutta based GCQ. We want to generalize this, especially in implementation, the improvement in the implementation to more general sectorial problems. The quadrature for the local term is still expensive. And okay, we think there is some room of improvement there, but it's not so clear how to do that. And okay, there is still some room for improvement in the algorithmic point of view because we still have some memory for more general sectorial problems, some memory issues. And we would like to see how much we can push our new analysis to see if we can improve the theory for hyperbolic problems. I don't know, but maybe for hyperbolic problems with damping or so. And for sure, the development of adaptivity techniques, there is a lot to do there still. So thank you very much for your attention. I hope I did not exceed my time too much.
No, it's okay.
That's all.
Okay, so thank you very much, Maria, for this very nice talk. So let's ask the audience if they have some questions or comments. So you can use chat or microphones to ask questions, please. Go ahead. I think Juan opened microphones for the questions.
Something in the chat? No.
No, it's Juan just selling the audio. So just a curiosity, Maria. So you told that the order of convergence is 1. So can we expect to have a more order of convergence?
But if you use as if the underlying solver is implicit Euler, not. But this is like the first step to develop the theory. Still, if your data is not regular enough, you don't achieve high order even if you use a high order method. But the thing is that you can actually apply a higher order method and refine your graded mesh. So often what you can do is to devise a graded mesh with the parameter gamma much stronger. And then if you use a higher order method, you can maybe see order 2 or 3. So actually we're working on that.
Okay. Okay, thanks. Are there other questions? Comments? Someone drawn the line, no? So it wasn't you, no, Maria?
I don't think so, but I'm not sure. No, I don't think I did.
So we tried to control, but I'm sorry about that. So probably some weird people connecting. So we apologize about that. Okay, so thank you so much for for giving a talk, and
thank you very much for
yes.
your attention. Also because it's probably a topic a bit outside
No, it's
the.
very interesting for non-local terms, for integral equations. So yeah, thank you.
Thank you.
So